Okay. Hi, can you hear me well? Perfect. I will do it in English, but if you want me to explain something in French, just let me know. Okay, let me start my timer. All right. So I'm going to talk about the local limits of random trees. I'm going to take the simplest case, the most, what we call the generic trees or uniform infinite planar tree. And, okay, let me show you an overview of what I'm going to do. So I will first introduce trees. I'm sure some of you have seen them before, but I don't know. It's just, I'm going to talk about a very basic classification of trees. And then I'm going to take the ensemble of trees, of rooted planar trees, to be more specific. I'm going to tell you what it is later on. And I'm going to put a metric on it. So we're going to get a metric space. And after we get this beautiful metric space, I'm going to start talking about limits. So this talk is about the local limits, but there is another type of limit that is very popular actually in the research in random geometries, which is the scaling limit, which is not yet my expertise. But I'm going to try to give you the idea of the main difference between the scaling limit and the local limit so that you get the spirit a little bit. Then I will concentrate on local limits, but of course, when we want to compute local limits, this is a problem of probability and probability distributions or probability measures if you want. But when we want to do that, when we try to do that, there are of course different questions one needs to answer because we need different tools from analysis and from combinatorics whatsoever. So I'm going to try to put these different elements of the story together to come to a conclusion and show you how the local limit that is called uniform infinite planar tree looks like. And but if you're not interested in probability, you can still get some nice things if you like analysis, for instance. So stay with me if you can. And I will try to conclude, if I have time, with what kind of modifications can be done. Okay, let's talk about trees first. Why do we want to work with trees? Trees are connected graphs without cycles. It's very simple. I can give you a combinatorial definition, but I'm not going to do that to keep it as simple as possible. And they are fundamental objects in graph theory, in combinatorics, and we like them very much when we do probability. But also computer scientists, in theoretical computer science, they like it very much. You can imagine why, because they can be used in the search algorithms, especially binary trees and so on. And physicists, they like it for different reasons. If you come from some kind of physical background, for statistical mechanics, or for they were popular in the studies of non-perturbative quantum gravity toy models as well. Okay, so let me give you a very basic classification, what kind of trees, when you see a tree, so that when you see a tree, you can identify what kind of tree it is. Of course, there are more elaborate trees, but I'm not going to talk about them. So they can be rooted or unrooted. What do I mean by rooted? It means that, okay, take a tree, which means take a graph without cycles, okay, which is composed of vertices and edges. And then mark a vertex, choose a vertex, and say, okay, this is my root. And then using the graph distance, you can actually understand this tree as a sequence of generations. You can say, okay, my root is the 0th generation, and then the children of my root are the first generation, and so on and so forth. Okay, this is a very nice thing to deal with, because once you do that, you get rid of all the symmetry factors that you have to take care of if you don't choose a root. And also this gives you the possibility to construct them recursively, and we will get back to this idea of recursion. So the second thing that it can be classified through is whether they are planar or unplanar. Okay, all the trees, you can always embed them into the plane, which means you can always take a tree and draw them in a way onto the plane, which means actually they're all planar graphs. But what we mean by planar is that when you start considering all possible embeddings of a tree. What do I mean by that? Here is a picture of it. For instance, let's take a tree. Let's say it's rooted. So take this one and this one. Let's say they are the root. And then you can say, okay, then the root has one child. That child has two children, and then one of these children has 3 children, one of that children has 2 children. So there are 2 ways to embed this tree into the plane, which you see on the photo, on the picture there. So if you consider all the embeddings, then this is gonna be, these trees are gonna be planar. And there is a third category for classification, which is labeled or unlabeled. Okay, there are many, many ways to label trees. This is the simplest way, that you label the vertices. If you have 3 vertices, you label them from 1 to 3. And this is, for example, there is only one tree of 3 vertices and 2 edges. You know, like you have 3 vertices and you connect them, and that's it. But if you say, okay, then I want to label them from 1 to 3, then you will end up with 3 different trees. So you will end up with a bigger ensemble. Of course, you can label them in all different sorts of ways, and label trees are very useful in the study of, for example, planar maps, and so I'm not going to talk about it, but they are important. Okay, so I talked about planar trees, then I said that you consider all the embeddings, but there is a specific terminology that we use when we say rooted planar tree or planar rooted tree. Sometimes I use that, sometimes I use the other. What we mean is a rooted tree where the children of each vertex is ordered from left to right. So this comes from the combinatorial definition itself. What do I mean? I say, okay, it has a root, and root has the children, and then I can say, this is the first children, this is the second, this is the third, blah, blah. And I order them from left to right. Once you do this, this gives you a very natural embedding into the plane, of course, because then you can draw the first child to the left and then the second to its right. So this is not the same thing as considering all the embeddings, because this one, by definition, has a very natural embedding. And these trees, rooted planar trees, are the trees that we will be considering for the rest of the talk. Okay, so when I say trees, I always mean rooted planar trees, okay? So I work in the probability group here. I will be working in the probability group here. So what do I want to do? I want to do probability with these discrete objects. Okay, but before starting doing probability, let me put some more structure onto this ensemble of trees, okay? Now we have all these trees. So far, so good. Let me put a metric on it. And let me introduce some notation. Okay, so this Tn is the set of trees that have volume n. By volume, I mean number of edges. You can also say number of vertices, they differ by 1. If I take this union from n is equal to 1 to infinity, I get the space, the ensemble of all finite trees, which I denote by T fin. And if I take the union with the set of infinite trees, which is the completion of this set of finite trees, I get the full space, T, okay? So let's denote the vertex set at graph distance s from the root by ds of t. For example, okay, let's look here. I have a tree here, T0. And if I want to say d3 of T0, it's going to be these vertices here that are at distance or at height. By height, I mean the distance to the root at height 3 of my from the root. Okay, so one more notation. The subgraph BR of T of a tree T is the subgraph that is spanned by the vertices that are at most at height R from my vertex, or at distance R from my vertex. Here is an example. So if I have a tree, there can be anything else on top of this. B3 of T0 is the subgraph that you see up until the height 3, okay? So once I have these definitions, let's say, I can now define a metric, which is noted by dist. So two trees, T and T prime. The distance between them is given by the inverse of R, where R is the distance up until which these two trees agree. So here, for instance, there are two rooted planar trees. They are the same up until the height 3, and then they differ. So the distance between them is given by 1/3, simply. Okay, so the information about this the metric, I mean, I construct the metric such that it encodes the information of the structure around the root of each tree. Okay, and with this metric, it becomes a separable and complete metric space. It's nice. then what I can do is, of course, this induces a topology, and then I can talk about the balls around a tree. So let's say I have a tree T0. The ball of radius 1 over r around T0 is given by all trees in my ensemble that agree with T0 up until height r. Okay? So this is a depiction, if you want. So this, let's say, is T0. And the B1 over 3 of T0 is going to be all the trees. So these red bubbles, there can be any kind of tree. It's free. Okay? So all these trees is going to be in the ball of radius 1 over 3 around my T0. Okay. I said I'm going to talk about local limits, but I want to tell you the difference, because you're going to encounter scaling limits if you go into this field, and I want to tell you the difference in spirit between the local and scaling limits. So they're actually the idea, I mean, although sometimes the techniques, they are kind of similar, the spirit is quite different. So, but what do I mean by limit, first of all? Let's talk about that. So whenever I have some kind of discrete objects, let's say I have the ensemble Tn, all the rooted planar trees of volume n, okay? So I have these discrete structures, and on a finite set, it's very easy to define a probability measure on a finite set. I can take the uniform distribution, for instance, and I'm given some kind of probabilistic structures on these finite sets. I want to understand what happens if I take this n to infinity. So I want to understand what kind of trees I would get if I let these trees grow bigger and bigger. Okay? So we are always interested in bigger structures, of course, the larger structures, if we start with these finite objects. So in case of scaling limit, you choose an object T, let's say this is going to be a random variable, uniformly at random inside Tn, the set of trees of volume n, and it is now it is known that if you scale this properly or suitably, let's say, then this converges, this approaches a continuous structure, and an example of which is seen in the picture. So you start with these discrete objects, and then you make them grow, you let the number of edges go to infinity, but at the same time, you somehow scale the distances, scale the lengths of these edges, so that when you do this simultaneously, what you get is a continuous object in front of you. So this is like having these trees and taking a distance and looking at it from very far, and you scale it so that you see something like continuous and finite in front of you. So this is kind of a global limit. You see the object globally. It gives you a global idea. So there is a reference if you want to learn more about these things. Okay, but what about the local limit? The local limit is different in spirit. Why? Because we don't scale distances. What we do, we just let the number of edges go to infinity. So the objects we get at the end, they are still discrete. And what we do, we study the convergence of arbitrarily large but finite neighborhoods of the root. So what you get in case of local limits is not this global picture that you can just take a distance and look what it is, because they are discrete and they are infinite. However distant you get, you cannot see the thing as a finite object in front of you, but rather you get the information around the roots of the trees. So imagine as you sit on the root of every tree and you look around and you see, okay, what kind of thing do I see around the root? Okay? So it is more of sitting on the root and looking what you can see around the root. So this is what we're going to deal with. How do we deal with it? There are multiple ways which are equivalent, but maybe different to formulate. But what I will concentrate on here is through constructing a sequence of probability measures on these finite sets Tn, and then try to construct a limiting measure, which is going to be the weak limit of the sequence of probability measures. And that weak limit is, of course, going to be supported on the set of infinite trees, because I take n goes to infinity, right? I take the limit n goes to infinity. So it is just a reminder what weak limit is. I guess you've seen it before. And we're going to do it for this for this sequence of probability measures, mu n, that I'm going to define in a minute. Okay, so we have some facts about this metric space. Any ball in T is both open and closed. This is a nice property that gives us some possibility to, I mean, it gives us some, how do you say, it makes it more easy to deal with this limiting measure, let's say. Two balls are either disjoint or they're contained in each other. Okay, this doesn't mean anything as it is, but you will see why it is important. And the set of finite trees is a countable dense subset of the whole space, okay? These are some facts. Let's leave them there. So now I just want to introduce you a lemma, which is a collection of some theorems from standard results from the convergence of probability measures. It's just a combination. I mean, don't concentrate on the writing because it's a bit like too much, I know, but I wanted to put it there. So this is a lemma that tells you under what conditions you can construct a limiting measure mu on the set of infinite trees, okay? So I start with the sequence of measures on these finite sets Tn, and I want to generate the weak limit of this. I want to construct a limiting measure that is going to be supported on the set of infinite trees, and this lemma tells you a strategy to do it. It's just a strategy. There are other ways to do it. Okay, so this condition 1 and 2 are about what kind of subsets that you want to use when you want to construct this measure. And then the third condition tells you that the sequence mu n of A are these subsets that I'm going to tell what they are in a minute. If they converge, given that the sequence of measures is tight, this lemma then tells you that the weak limit, the limiting measure, exists. And if you're lucky, you can also analyze its properties. Okay, what do I mean by tightness? It means that for each epsilon, there exists a compact subset of my space such that the mass of the complement of this compact subset with respect to mu n is smaller than epsilon for all n. So basically, it is approximating, of course, all these things by compact subset from inside, right? Okay. The set that satisfies the conditions 1 and 2, a set that satisfies the conditions 1 and 2 in this lemma, is the set of balls. Okay, we are lucky. So we will just look at the convergence on balls, because remember, the third condition says that they have to converge on these subsets, and these subsets are the set of balls. And if they converge on balls, if this sequence of measures, it converges on balls, and if I can show that this sequence of measures is tight, then I get the existence of a limiting measure. Okay, and I just want to remind you that you again actually somehow encounter the word local here, because this tells you actually your measure is fully characterized by its value on balls. So it is a local information. So the local information that you have about the convergence on the balls gives you the whole information about the limiting measure. And this also means that the whole information that you have about this limiting measure is actually a local information that you have on the values of the balls with respect to this measure. Okay. So now we have an algorithm. We need to show tightness, and we need to show the convergence on balls. So far, so good. And but I still have not told you what sequence of measures we want to start with. The most typical one is the uniform measure. So what do? I take Tn, the set of finite trees of volume n, and then I can count them. There are a finite number of them. And this number, I say it is Cn. So Cn is the number of trees in Tn. So I just say, okay, then mu n of t, when t is in Tn, is given by 1 over the number of trees in my set. So it's 1 over Cn. So it's the uniform measure. So once I have this, remember the algorithm, I have to show convergence on balls. So to be able to calculate the mass of the ball, mu n of this B1 over RT, we need to understand one more thing. We need a tool. Okay, these finite measures, 1 over Cn, the measures, the uniform measures on Tn, they are basically defined by these numbers Cn. And I want to let n go to infinity somehow, in a way, right? So what I want to understand then is how these Cn's look like if they are very big, if when n goes to infinity. So I want to understand their asymptotic behavior. So now comes in to the story a very nice tool that that makes use of more analytic of analysis, for mostly complex analysis, to understand the asymptotic behavior of these coefficients. So what do we do? Okay, so we have a sequence of uniform measures. We want to show they converge weakly to a limiting measure. And for that, that's not me. And for that, we want to understand how these Cn's look like asymptotically. So how do I do that? First thing that we do, we encode them. So I'm sure you heard already the concept of generating functions. So I encode these Cn's by a generating function. I define z of g as the sum from n to infinity of Cn g to the n, where g is a complex number, okay? It's a complex variable. And then I will work on it, where it converges, and if it has a singularity, what kind of singularity, so on and so forth, okay? So if I have this generating function, and then I can look at its radius of convergence and its singularities, its analytic structure, it means that somehow I took a combinatorial problem, which was counting the number of trees of a certain volume, and I turned it into an analytic one. Okay, now let's try to, okay, how do we compute this generating function zg? So let me put it verbally. It's called the symbolic method in the language of analytic combinatorics, which deals with these things, that mapping these combinatorial problems onto analytic ones and solving them with complex analytic techniques. A tree, what is a tree? A tree is a root. Okay, the root vertex always has valency 1 in my notation. It's just a technical assumption. You don't have to do it, but it is like that, let's say. And I associate the variable g to every edge, okay? So a tree is a root to which I associate a variable g, together with a sequence of trees that are grafted on this vertex here. So you see a picture, you have to sum these over. It says, okay, this tree can be the tree that has only one edge, g, plus g times one tree that I graphed on this, which is also generated by my generating function z of g, plus I take again this root edge, then I graphed two trees, which are also generated by this generating function, so on and so forth. Okay, so if I take this sentence and I write it, I want to write it down, I want to formulate it somehow mathematically, this is what you get. Z of g is equal to g plus g times z of g, the root times whatever I graphed one tree on top of it, plus z of g squared plus z of g cubed, so on and so forth. Very simple, huh? And then, okay, you can sum it over, given that it converges, let's say, and you get g over 1 minus z. And okay, this is a very simple equation. You solve it. It has two roots. You choose one of them. You choose the one that will give you positive Taylor coefficients, because you want this to encode the number of trees, and number of trees cannot be negative. Huh? Okay, so I get this generating function, which is super simple, 1 minus square root of 1 minus 4g over 2. Great. Okay, good. I have something now, and this converges, I mean, as long as the norm of g is smaller than 1 over 4. Okay, so I have this thing that is analytic in this disk. Perfect. So just a notation, I note the nth coefficient of zg by this parenthesis g to the n zg, which is Cn, because this is how I encoded it. This is how I defined my z of g. And if I now can expand this function and look at its nth coefficient, then I have the number of trees in Tn. Perfect. And I denote it by a to the n theta n, where a to the n is, of course, the exponential growth factor, and theta n is going to be the sub-exponential growth factor. It can be a power of n, square root of n, logarithm of n, so on and so forth, okay? So, I mean, you see that this function has a branch cut at g is equal to 1 over 4. And this nature of the singularity is going to give you an information. This is, I mean, these things you can find in the book Analytic Combinatorics. I'm going to give you the bibliography at the end. But this is called the principle of coefficient asymptotics. Okay. So whenever you have a generating function, it has a singularity. Its singularity dictates the exponential growth factor of its coefficients, which is a to the n. And its nature here is a branch cut. What kind of singularity it is? This information tells you how the sub-exponential factor looks like. I mean, this is a great thing, because I started with this combinatorial problem. I want to count trees. I wrote down a generating function. And then what I have to look at is just a singular behavior, singular structure of my generating function. And I'm going to get all the information about these coefficients. Okay, so this is a standard theorem, which is one of the simplest of the transfer theorems, which tells you how to get these, the asymptotics of these Cn's once you are given a generating function of this form. Here our x is going to be 4g. Remember, we had 1 minus square root of 1 minus 4g over 2. And alpha is going to be equal to 1 over 2. So if you put these, it's alpha is equal to minus 1 over 2. Sorry, it's a typo. If you then substitute these information, these given factors into the theorem, whose proof you can find in Analytic Combinatorics book by Flageolet, then you get the asymptotics of these Cn's, which is given by 4 to the n to the minus 3 over 2. So remember that I said that the location of the singularity gives you the information about the exponential factor, and it was at 4g. And if you think about it, then 4g is equal to x. So what you have to do, you have to scale it by 4 to the n. So where it was, where g is equal to 1 over 4, where the branch cut was, what gives you the information about this exponential behavior, and the sub-exponential information comes from the type of the singularity. Okay, so what did I want to do? Let's remember. I started with a sequence of uniform probability measures. I wanted to construct the limiting measure mu. And to construct this limiting measure mu, I had an algorithm that told me to show the convergence on balls and to prove tightness. Okay. So what do I mean by convergence of balls? I mean, I'm not going to give you the rest of the calculation, but the idea is what you see there on the slide. So mu n of b1 over r of t0. Let's say this is t0 here. You have the t0, and you have whatever can be on top of it. Any tree can be grafted here, right? Given that the total number of edges of all this structure will add up to n plus k minus n0. I mean, plus k is just it comes from some convention. It doesn't matter. Okay, but what I want you just to see, I'm not telling you to understand this fully at the moment, but you have these numbers Cn, and you want to take this n to infinity. So what we actually did was a good thing to do to understand the asymptotic behavior of these Cn's, because you see, I need them here. Okay? So now you have to play with these things a little bit to compute this expression, and then take the limit n goes to infinity. But you need a couple of pages of estimations using some complex analysis, let's say. And what you get at the end is this expression. Okay, actually what I wanted to do is just to show that this converged, but I got something better. I actually found what it converges to. I have an expression. So I have the mass of the balls with respect to my limiting measure mu that I will denote by mu. Okay, so actually we now arrived to our limiting measure that is called Uniform Infinite Planar Tree. Why uniform? Because it is the limiting measure of the sequence of uniform measures. This is why it's called uniform. It is infinite because I took n goes to infinity and this measure is supported on infinite trees. It's planar because I started with planar trees and it's a tree. Okay. So it's the uniform infinite planar tree. Okay, but now you can ask something. You can say, I have the measure, and you told me that this measure is actually fully characterized by its value on the balls. And I have the value on the balls. It's 2k times 2 to k times 4 to the minus n0, where n0 is the volume of T0 on which I grafted these things. So if you know this, you should be able to analyze its properties, which means, like, what does it look if I take a tree from this ensemble, from the support of this measure, what does this tree look like? You can ask this question. And as you have the information of the mass of the balls, you should be able to answer this question because this characterizes the measure fully, right? So we do actually know how they look like. They look like this. They are single spine trees. So the trees that you will find in the support of this limiting measure mu, whose existence we showed, they look like this. They have, this is the root. They have a single spine. What do I mean by a spine? I mean the unique infinite path in this tree. And then you have some finite trees that are shown in red here, sticking out of these vertices on both sides of the spine. Actually, these finite trees, they are distributed independently, by which I mean that their distribution does not depend on the distribution. I mean, they're all distributed actually identically and independently, according to what we call the Bienem-Galton-Watson tree. I mean, if you heard about it, it's good, but if you didn't hear about it, it's fine. I mean, it's just it's a measure on the set of finite trees, Stephen. So you will only get finite trees out of this. You will only get finite trees sticking out of this spine, and you have one infinite spine. I mean, if one of them was infinite, then you wouldn't have one single spine, right, anyway. Okay, so this is how they look like. Now it is almost at the end of what I wanted to say, but I want to close with by saying something about what I did up until now, because, okay, like, it's nice to say it. So we did the simplest case, I said. What did we do? We started by this sequence of measures that are uniform on Tn. And you can, of course, ask, okay, what if I start with a sequence of measures that are not uniform? That if I don't take, what happens if I don't take the uniform distribution? What if I take something else? Do I get the same object at the limit? Do I get the same limiting measure? You might get the same limiting measure. I mean, there are many cases that you get the same limiting measure. I mean, the same kind of tree with single spine and finite trees around it. But there are also cases that you can actually end up with a different local limit. And different limits are always interesting. So here, what the idea is to start with the sequence of measures that also takes into account a weight factor that depends on the height of the trees in these finite sets Tn. So what do I mean by that? I mean nu n of t, lambda is a real number, it's a parameter, of t of a tree t in Tn, this is a tree of volume n. It is given by this exponential of minus lambda h of t. H of t is the height of my t. It's finite because t is finite. Over Wn. Wn is just the normalization factor, what you get if you sum over all these weights. So this is what we call height-coupled trees, or trees with height-dependent weights. This is a global coupling factor that you give to your tree. And what happens is that if lambda is equal to 0, obviously you get the uniform infinite planar tree. It's the case that we just covered. If lambda is smaller than 0, you still get single spine trees, but these finite trees that are around this spine, that are grafted on this spine, they tend to be even smaller than before. They're still finite, but they're smaller than in the case of uniform infinite planar tree. And it kind of makes sense, right? Because if you choose lambda to be smaller than 0, this factor exponential minus lambda ht actually tells you to favor the longer trees. So you actually push them to grow longer before they can spread out. So you get thinner trees in the limit that have one single infinite spine. But what if you do the other way around? What if you try to suppress them? So they want to grow, let's say tall, but you tell them, no, okay, if you're very tall, I'm not gonna favor you. So this is what happens, of course, if lambda is greater than 0. You have this exponential factor. If ht is larger, then you have a smaller weight that is associated to that tree. And what happens at the end is that in the limit, you get an object that doesn't have a single spine anymore. So you oppress them, but they find multiple ways to reach infinity. Instead of following one single way, they find multiple ways to reach infinity. So here in the picture, these red blobs, they represent infinite trees, which can also have multiple infinite spines. And under that, this is what we call a backbone. So now the spine is not just one infinite path, but it will have multiple possibly infinite paths. And then you have finite trees that are sticking out of the vertices on this spine, the new spine, which is not a single spine. And yes, so this is the result you get if lambda is greater than 0. The techniques that are used, I mean, the idea to generate this result is basically the same. I mean, you see that the idea is very simple. You employ the same idea. You can use the same lemma whatsoever. But the techniques that you have to use to compute the asymptotics of these factors in the generating function, if I write down now the generating function for these trees, that the factors, these CNs, are not going to encode now the numbers of trees, but it's going to encode the weights, the weighted factors of these trees. It is a bit more involved to generate, to find out the asymptotic behavior of these functions, but the idea is basically the same. You follow the same strategy, you try to compute a similar thing, and analyzing it is a bit more cumbersome, but it is what it is. Okay, and the archive number is there if you want to take a look at it. Thank you. Okay, it's a probability measure on the set of trees. So and its information, as we saw it before, it tells you, you take a tree, you look at the ball around it, and in this ball, there are also other trees. So the objects on which this probability measure is supported are trees. So it's supported on the set of infinite trees. So it's a probability measure on the set of infinite trees. So what it tells you at the end is how the tree, because see, okay, let me show you the expression again. So here, this k is the number of vertices here, 1, 2, 3, 4, blah, blah, on which you graphed. Let's say this is T0 and this is what you graphed. You look at the ball around this. So k is the number of vertices at the top height of this T0. So actually, and N0 is the volume of T0. So actually, the mass of the ball is given by the properties of the tree that around which you look at the ball. Yeah. Is it okay? Okay. Great. Yes, please. Yes. The vertices that are called infinite type vertices, which means that these vertices have an infinite path that is going through them, or they have infinite number of children, let's say. At each level, they are Poisson distributed. So you know actually the mean of the number of infinite vertices at every height. I mean, once you have the information of the mass of the balls, you are supposed to be able to derive all kinds of properties of this measure simply because this is the information that the measure carries, and this is all. So yes, we know. I mean, we know how to profile the number of the average number of vertices at a certain height. You can easily calculate it. Thank you. Yes, this is, I mean, you know it's Poisson distributed. So you know that, at a finite, if you look at the average number of infinite vertices, so because this is gonna give you the number of vertices who are on the spine at a certain height, it is finite, of course. But overall, then if it has infinite number of spines, you mean? It of course depends on what you. Yes, I mean it depends on what height you look at, like how many backbones start from that height, and then the number of these backbones is of course finite. Yes. Okay, real trees, they never grow infinite, right? So I don't know, but I mean you had this picture at the very beginning. Actually, you can somehow. I mean, if you really, sentimentally you can relate it, but you know, not in the real sense, of course not, because they don't grow infinite, but you can observe some different patterns, right? I mean, this looks more like it spreads out at the, you know, I mean, this looks like it likes growing taller rather than getting wider. Okay, you can in a way, but you know, but not really, no. Yeah. Thank you.